All right, hello, and welcome to Monday Night Office Hours. It is the only office hour we'll be holding this week because Wednesday is Veterans Day, so we all get the day off. So as per usual, there's no pre planned agenda for tonight. I just checked my emails right before starting, and there's no questions about anything. At least didn't receive any over email. So I am here, as always, to answer any questions that you may have. And in the absence of questions, I will just be here hanging out, checking emails, doing class stuff. But please interrupt me at any time. I would much rather talk about chemistry with you than do class-related tasks. Ah. Lauren, I so totally can. Here, let me log into my textbook real quick. All right, let's see, chapter 7. Chapter 7, number 43. Oh, wait, hang on. That's actually on the right page. There we go. Okay. Chapter 7, problem 43. Let's take a look. So a laser pulse with a wavelength of 532 nanometers. So here's our wavelength is 532 is not 33. 532 nanometers is our wavelength. All right. And this laser pulse contains 3.85 millijoules of energy. How many photons are in the laser pulse? This is a great question. Kate, we will totally hit those problems next. All right, so let's see. Okay, so here's the deal. So this problem, excuse me. This problem's interesting. Let's identify what we're trying to find. And we were trying to find the number of photons in the pulse. Right? Number of photons in the laser pulse. Let's look at what we're given. So we are given the wavelength of one photon. So this is the wavelength of one photon. And we're given the total pulse energy, which is equal to 3.85 millijoules. All right, now there's a couple things that that should instantly kind of trigger your memory banks, and that is we're given a wavelength and we're also given energy. As we know, the energy of one photon of light, is equal to Planck's constant times the frequency, right? And frequency times wavelength is equal to the constant speed of light. Now, if you divide both sides of this equation times wavelength, it rearranges and you get an expression that says frequency is equal to the constant speed of light divided by wavelength. And you can substitute this frequency into this equation, so you get energy is equal to Planck's constant times the constant speed of light over wavelength. That's a little sloppy. I'm going to draw that a little clearer. All right. And so this equation then rearranges. We can write energy is equal to Planck's constant times the constant speed of light over wavelength. But here's the important thing to remember. This is the energy of one photon. All right? This is the energy of one photon. And this is the energy of all the photons. All right? That is the energy in millijoules of all the photons together. So if you took your energy 3.85 millijoules, or actually here, let me make a little more space here. So here's the deal. So we know what our total energy is, and we can find the energy of one photon. So if you divide the energy of all the photons together by the energy of one single photon, that'll tell you how many photons are present in the pulse. So we're going to take the energy of the pulse and divide it by the energy of one photon, but first we need to find what that photon is, the energy of that photon. Oops, we're still working number 43. All right, so we have energy of our photon of light is equal to Planck's constant times the constant speed of light divided by the wavelength. Planck's constant H is 6.626 times 10 to the negative 34th. Energy, the units are joules times seconds. Speed of light is 3.00 times 10 to the 8th meters per second. Now the frequency, the wavelength is 532 nanometers. The problem is right here. Nanometers and meters will not cancel. So we need to convert 532 nanometers to meters. So nanometers in the denominator, meters in the numerator. 1 nanometer is 10 to the negative 9th meters. Nanometers cancel, and we get our wavelength is 5.32 times 10 to the negative 7th meters. Now, whoops. When we put in our wavelength in meters, our units will cancel. Meters is not the only thing that cancels. Our time units, seconds, cancel as well. And now we're ready to crunch our numbers. So 6.626 times 10 to the negative 34th times 3 times 10 to the 8th divided by 5.32 times 10 to the negative 7th. So energy here is equal to 3.74 times 10. Let's see. Times 10 to the negative 19th joules. And this is energy per one photon. All right. Our total energy we were told was 3.85 millijoules. But just like we did for our length, we need to have the same energy unit. So we're going to multiply our total energy by unit conversion so that our units will take care of themselves. So 1 millijoule is 10 to the negative third joules. So our total energy in joules is 3.85 times 10 to the negative third joules. All right. Now, that's our total energy. That's the energy of one photon. If we divide our total energy by the energy of one photon, we will have the number of photons in the pulse. So we take our total energy, 3.85 times 10 to the negative third joules over 3.74 times 10 to the negative 19th. And this is joules per photon. You'll notice joules cancels joules. And then we go 3.85 divided by 3.74. Is equal to 1.03 times 10 to the positive 16th photons. So this right here this is the number of photons in the energy pulse. Totally. Lauren, you are so welcome. Awesome. That is great to hear. Okay, let's see. Let's jump to chapter 9 for a couple problems from chapter 9. Let's see. Okay. Oh wait, no, sorry. Wrong one. Let's see. Okay, yeah. All right, so these are from chapter 9. And this first one is 37B. All right, so for actually, oh, there we go. All right, for 37 and 38, they ask us to write a Lewis symbol for each atom or ion. Let's see, 37B is an ion, and 38C is also an ion. Okay. So for 37B, we need to write the Lewis symbol for sodium. Sodium cation. All right. Now, a very similar strategy to the one we used for doing electron configurations. First, we're going to find and write the symbol for just sodium. And then we're going to adjust our electron count based on the charge. All right, so sodium is in the first column of the main group. That means that it will only have one valence electron. So sodium, the atom, will just have one single dot in its Lewis symbol. Sodium cation, however, has a positive charge. This positive charge means lose one electron. So the Lewis symbol for sodium cation needs to have one less dot in its structure than sodium atoms. So that is the symbol for sodium cations. So it's just Na plus. And you'll notice actually it's a very similar problem. Oops. It's a very similar problem for number 38. Let's see, 38C. I think you said, yeah. All right, so for 38C, we need to write the Lewis dot structure for magnesium cation. Now, if you just look up magnesium, it's right here. It is in the second column on the periodic table. So magnesium atoms will have two dots in their Lewis symbol. The positive 2 on the cation means that it needs to lose 2 electrons. All right. So magnesium cation 2 plus will have a Lewis symbol with 2 less dots than magnesium atoms. So that is the Lewis symbol for magnesium cation. Oh, yeah. Kate, that is so stinking kind of you to say. And one thing that I do know is you are going to have a total blast in Chem 401. It has some of my absolute favorite parts of Gen Chem are in the second semester, especially the stuff with kinetics. You'll be able to get back to thermodynamics again, which is cool, and get kind of a deeper, more rounded understanding of that topic. You'll get to talk about entropy, not just enthalpy. In addition, you also get to do a bunch of stuff with equilibrium, so studying when a reaction is reversible, how reversible is it. It's some of the coolest stuff out there. So I would love to be able to obviously to have you in the class to teach it, but my assignment is Chem 400 next semester. So I'll be doing this again, and yeah, I know you're gonna have a blast in 401. Oh, okay, Kyle. Sorry, I just saw your comment. Let's see. Working on experiment 6. Question about sig figs. Ah. Rin, great question. Okay. I believe it's 10 to the 6th. But let me double check. Yes. So one megahertz is 10 to the 6th. Yeah. Hertz. Oh, great question. Yeah, sure thing. Here, let me, Anthony, let me find it. Oh! Okay, exercise. Okay, okay. Totally. Okay, here, let me... Okay, hang on. I've got a... That's in a different place. Let me grab it real quick. Let's see. Okay. Let's see. You wanted to see something similar to number 33. Oh yeah, dude. No, totally no worries. Okay. Okay. So okay. Let's write this up. So this is exercise 7. And okay, so for, and then specifically, this is number 33, and they give us an equation where calcium, solid calcium metal, reacts with oxygen gas to produce solid calcium oxide. And as given, this reaction is unbalanced, but we can balance it by multiplying calcium oxide and calcium by 2, and that balances this equation. All right, so number 33, they ask how many grams. All right, so that's the first thing. They want to know how many grams of calcium oxide can be produced. I'm gonna change the numbers, but you'll see how to solve this problem. How many grams can be produced from let's go with 200.0 milliliters of oxygen at 85 degrees Celsius. I'm going to change that actually. I'm going to 85.00 degrees Celsius and 1.62 atmospheres. All right. So here's the deal. You'll notice that they give you a volume, a temperature, and a pressure for your gas. All right. And then they ask you to find a mass of calcium oxide. So we're given a volume, a temperature, and a pressure. A volume, a temperature, and a pressure. Now here's the thing. You always know what the ideal gas law is. Ideal gas constant is R. R is just a constant, it doesn't change. So we have enough information to find moles of oxygen. And then once we know what our moles of oxygen are, we can use the fact that in this balanced chemical equation, it is a 1 to 2 mole ratio of oxygen to calcium oxide to convert moles of oxygen to moles of calcium oxide. and then for moles of calcium oxide to grams. So that's the plan. That's the strategy. It's going to start with finding moles of O2. So R and T cancel. We find that moles, and specifically, this is moles of oxygen, is equal to pressure times volume over R times T. Now, couple things. We need to do a unit conversion on our volume unit and our temperature unit, because when you write out your value for the ideal gas constant R, it's 0.08206. And this is liter atmospheres over mole Kelvin. So volume's got to be in liters, temperature's got to be in Kelvin for this thing to work. So we got to do a couple unit conversions. First we take 85.00 degrees Celsius and we add 273.15 to convert to Kelvin. And I'm going to use my calculator for that. 85 plus 273.15 is 358.15 Kelvin. That goes in my denominator. 358.15 K. And then in our numerator, we have our pressure, 1.62 atm, times now our volume, 200.0 milliliters, needs to get converted to liters. And there are 1,000 milliliters in a liter. So this comes out to be 0.2000 liters. All right, 1.62 times 0.2 divided by 0.08206 divided by 358.15. All right, so this comes out to be let's see, we can have three sig figs, 0.011022424, and this is moles of oxygen. Now we can have three sig figs, so I'm going to put three lines there to remind myself, but I'm going to wait around till the end. So first step, we want to convert from moles of oxygen to moles of calcium oxide. And it is a 1 to 2 conversion there. So moles of oxygen cancel. Next, we need to convert from moles of calcium oxide to grams of calcium oxide. Now, calcium, let's see, I know it has an atomic mass of 40 point something. Let me bust up my periodic table. I think 40.08. Yep. Oxygen is 16.00. So this is 56.08. 56.08 grams of calcium oxide are in 1 mole. Now moles of calcium oxide cancel. And we're ready to crunch some numbers. So we have our moles of oxygen times 2 times 56.08. This comes out to be 1.23647.876. But we got to round to 3 sig figs, which is, I guess, kind of sad, because 6 is going to round up, ruining our magical 123. So 1.24 grams of calcium oxide is the mass that can be produced from the amount of oxygen that we were given, given that volume, temperature, and pressure. Anytime, dude. Thanks for coming by and asking. I do not mind at all. Ah. Totally. You totally apply the rules for sig figs when you are converting Celsius to Kelvin. Which is why, for example, like with the previous temperature conversion, when we took 85.00 degrees C and converted it to Kelvin, so when you punch it into your calculator tells you that the answer is 358.15. But when you look at sig figs, since we did addition, our last sig fig for 85.00 is in the second decimal place. Same with 273.15. So here, our last significant digit must be in the decimal place, and it is. So it didn't require any rounding. Oh, okay, yeah. Anthony, that is 100% correct. STP are exact. They're exact values because they're not measured. STP is defined as 1 atmosphere, 273 Kelvin. So they're not measured. They're defined, which makes them exact. let me check Lab 7. I can't remember. I feel like I posted about Lab 7. Huh. Oh, snap. So sorry, my apologies. I made the page and everything, and then I forgot to publish it. So I'm gonna bump the due date back just a little bit because I thought I had made it all available, but I had forgotten to. So let me punch this back a little bit. Awesome. I'm glad this came up because I thought it was like good and published, and you know, everything is turning up roses. There we go. Okay. All right, so your question about the number of valence electrons, one thing you could do is look at so valence electrons are the number of valence electrons are the sum of all electrons in the highest energy shell. So one of the ways you could determine the number of valence electrons is by looking at the electron configuration. So for example, if you looked at, let's just say, antimony, the electron configuration for antimony has a krypton core, and antimony's on the fifth period, so this would be 5s2, 4d10, 5p3. All right, so that's the electron configuration for antimony. When you look at the highest energy shell, you're looking at the fifth shell, and we have 2 plus 3 electrons. So antimony, we would say, has 5 valence electrons. All right, so that's one way you could do it. Another way you can do it to determine the number of valence electrons that an element has, and I'm just going to move helium over, is and this is only for the main group elements, but you can look at the column it occupies in the main group, and that will also tell you, if it's a main group element, the number of valence electrons it'll have. So the first column has 1 valence electron, second column has 2, third has 3, fourth has 4, fifth has 5, sixth has 6, seventh has 7, and the eighth, or I should say, should go all the way down to neon, the eighth has 8. Those are the number of valence electrons for every element in those columns. I totally can go over number 17 in exercise 7. I'll change the numbers around and everything, but let's but I can totally work it. All right, let's see. So this is another exercise 7 joint. And let's see. You want to see number 17. All right. So let's see. Dalton solved partial pressures and mole fractions. Okay, they give us some background stuff. let's take a look at number 17. A mixture of gases exerting a pressure of 2.08 atmospheres consists of 0.28 moles of oxygen, 0.42 moles of H2, and 1.2 moles of carbon dioxide. What is the partial pressure of each gas? All right. So, all right. So there are, anytime you encounter these words, partial pressure, that should instantly set off to the two words that should appear in your mind are Dalton's law. All right. And Dalton's law has two formulations. The first is the total pressure of a mixture of gases is equal to the partial pressure, the sum, of the partial pressures of each gas. So the pressure of the first one plus the partial pressure of the second one plus ... however many things you have. That's one way to write it. The alternate way to write Dalton's law of partial pressure is the partial pressure of gas number 1 is going to be equal to the mole fraction of gas number 1 times the total pressure. And this thing right here is called the mole fraction. All right, the mole fraction. And the mole fraction has its own equation. The mole fraction is equal to the moles of gas number 1 divided by the total moles of all of the species involved in the mixture. And you'll notice that right here, we're given a total pressure, the pressure of the mixture. That's the total pressure. And we're given the moles of each component of this mixture. So we're totally going to use this version of Dalton's law because it's the easiest. It'll be easy to calculate all the mole fractions and determine our partial pressure because, again, we have our total pressure and we have enough information to calculate the mole fraction. So we're going to use that equation on each one of these gases. First, let's do oxygen. All right. The mole fraction for oxygen is equal to the moles of oxygen, 0.28, divided by the sum of all the moles of gas in the mixture. All right, so consolidating our denominator, 0.28 plus 0.42 plus 1.2 comes out to be in our denominator 1.9. You'll notice sig figs wise, our last significant digit needs to be in the first decimal place, and it is, so we don't need to round anything. We have 0.28 in the numerator. All right, so that is our mole fraction, which means our pressure of oxygen, partial pressure, will be equal to the total pressure, 2.08 atmospheres, times our mole fraction, 0.28 over 1.9. So 2.08 times 0.28 divided by 1.9. We can have two sig figs because our numerator and denominator here each have 2. So the partial pressure of oxygen for this problem, the numbers will be different for the one on the exercise, will be, this comes out to be 0.30652. Keeping 2 sig figs, the 6 is going to round up. Round that 0 up to a 1, so partial pressure of oxygen comes out to be 0.31 atmospheres. So for these numbers, that is the partial pressure for oxygen. Next, let's do hydrogen. All right, so the partial pressure of H2 is equal to the total pressure (2.08 atm) times the mole fraction, which is 0.42 over 1.9. So 2.08 times 0.42 divided by 1.9 comes out to be 0.45978. But we can only keep 2 sig figs because of our mole fraction. 9 is going to round up. So the partial pressure for H2 will be 0.46 atm. All right, finally, the partial pressure of CO2, which is equal to the total pressure to, 0.08 atmospheres times 1.2 over 1.9. So 2.08 times 1.2 divided by 1.9 comes out to be 1.31368. 2 sig figs, 1 rounds down. Partial pressure of carbon dioxide is 1.3 atm. Again, your numbers will be different for when you calculate this problem because I changed them around, but that is how you solve it. Lauren, sure thing. Let me pull it up real quick. Okay. Okay, here. Let me... All right, let's pull some stuff up here. Okay. Okay, so in this earlier in the the discussion, they define some reactions for us. So they call reaction 1 is the neutralization reaction between HCl and sodium hydroxide. Which makes water and a salt. They define reaction 2, which is the reaction between solid magnesium and aqueous hydrochloric acid to produce magnesium chloride, and so this is aqueous, and hydrogen gas. And then they define reaction 3 as a reaction between solid magnesium and water. To produce magnesium cations, hydroxide anions, and hydrogen gas. All right. So let's see. Sorry, I'm scrolling back down. All right. So let's write the net equations. So here's the thing. In this experiment, so you've got reaction 1 and reaction 2. And they each have their own change in enthalpy. Right? Delta H for reaction 1, delta H for reaction 2. But for reaction 3, for delta H3, they want us to use reaction 1 and reaction 2 with Hess's law to determine the delta H for reaction 3. All right, because the thing is, both of these right here, you measure / calculate in the experiment itself. You measure and calculate delta H1 and delta H2, so they want us to use Hess's law to determine the delta H for reaction 3. All right, so I'm going to, so that's kind of the conceptually what we're doing, what our goals are. Now I'll walk step by step through this. I won't use values for the delta H's, but I'll show you kind of how to symbolically get there. All right, so first off, we want to find reaction 3. All right, this is our goal. All right, we're trying to get here to solid magnesium plus, there's 2 water molecules. And this produces aqueous magnesium two hydroxide anions plus H2 gas. All right, this thing right here is our goal that we are trying to attain. We're trying to get here, and we're going to do it by using Hess's law, adding things together, subtracting them. So first, step number 1, they want us to write the net ionic equations for the first 2 reactions we conducted. All right, so let's go ahead and take a look at reaction 1. Oops. All right. Oh. Sorry, Photoshop is bugging out just a little bit. Sorry. So, okay, sorry, hang on. Photoshop is just a little frozen at the moment. Okay. Here, hang on. I really don't want to have to do a hard shutdown, but if it doesn't boot back up, I will. Okay, sweet. We are back. Okay. So sorry about that. That halt to the action. So, the first thing they want us to do is to write the net ionic equations for the 2 reactions. We're going to start with reaction 1. All right, so reaction 1 is looks like this. So we've got reaction 1. And we've got aqueous HCl plus sodium hydroxide producing water, liquid water, and sodium chloride, also aqueous. And this has a delta H that we're just calling delta H1. All right, now they say first step is to write the net ionic equation. Now, in the net ionic equation, you take every aqueous ionic compound and you separate them into their cation and anion pairs. So when we do that, we'll have HCl plus, we got to separate aqueous sodium ions plus aqueous hydroxide ions, producing liquid water, plus we got to split up sodium chloride, aqueous sodium, cations, plus aqueous chloride anions. And so far, we haven't done anything that will alter or modify our delta H. Now, the second part of writing a net ionic equation is you need to cancel all spectator ions. And here in this reaction, there's only one spectator ion we can cancel, and that is sodium. So sodium and sodium cancel each other out, bringing us to the net ionic equation of HCl plus hydroxide producing water plus chloride. Now, again, so far we haven't done anything to alter our change in enthalpy, but that's about to change. First, you'll notice that in reaction 3, it does have liquid water, but it has it as a reactant, and in this reaction 1, liquid water is on the product side. Now, if we want to find the delta H for reaction 3 using Hess's law, we need to put water on the reactant side like it is in reaction 3. So we got to flip this thing. We're going to flip our reactants and our products. So we get aqueous chloride anions plus water, which is a liquid, produces HCl, aqueous HCl, plus hydroxide. And whenever you flip a reaction, your delta H does not stay the same. When you flip it, you got to multiply the whole thing by -1. So you multiply the delta H for reaction 1 by -1, and that is the new delta H for this reaction. Now, the second thing you'll notice is we don't have one water molecule on the reactant side. We have 2. So we need to take this reaction and multiply everything in it by 2. All right, so we'll have 2 chlorides plus 2 water molecules in the liquid phase, producing 2 molecules of HCl plus 2 molecules of hydroxide. And now the delta H here, we got to multiply by 2 as well. So it'll be -2 times the delta H for reaction 1 will be the delta H for this new reaction. All right. Now this is getting us part of the way. You'll notice that we've lined up 2 moles of water on the reactant side and 2 moles of hydroxide on the product side. And that's as far as we can get with reaction 1. Now we need to do a similar manipulation with reaction 2. And I'm going to open a new slide to do that in. Let's take a look at how we can use reaction 2. All right, reaction 2 is solid magnesium plus HCl. Oops. Which is in the aqueous phase. Logan, I totally see your question, and I will hit it up once we finish working the one at hand. All right, so let's see. So reaction 2, and this produces aqueous magnesium chloride plus H2 gas. And this has a delta H that we're calling delta H2. All right. Now, let's write this as the awesome, dude. Thanks for being cool. We'll totally get there. We're actually pretty close to the end of this one. All right. So here we have, we were told to write the net ionic equation for this reaction. To do that, we have to split up every aqueous ionic compound. So when we do, we're going to split up magnesium chloride into aqueous magnesium cations plus 2 aqueous chloride anions plus H2. And you'll notice we haven't done anything to change our delta H yet. Splitting them up, writing a net ionic equation doesn't alter it. And there's no spectator ions to cancel at this moment in time. Now, one thing I do want to point out, though, is there are several features of reaction 2 that are advantageous. You'll notice that we have solid magnesium in place, we have magnesium cations in place, and we have H2 gas. All right, so now we're going to take this net ionic equation that we just wrote and add it with the net ionic equation / manipulated equation that we developed on the other slide. So just rewriting reaction 2, we've got solid magnesium plus aqueous HCl oh, hang on 1 second. Sorry. One thing that I messed up here is there's 2 moles of HCl here in the balanced chemical equation. That was just my bad. So there's 2 moles of There we go. 2 moles of aqueous HCl here, producing magnesium cations. Yes! Lauren, you're totally right. Totally. All right, plus H2 gas, and this came from reaction 2, and its delta H is delta H2, which you determine in this problem, or not problem, experiment. All right, hang on. All right, so that's reaction 2. Now with reaction 1, we did some manipulation of this one, some alterations. And we're going to use the kind of modified, manipulated equation that we developed, which was 2 aqueous chloride ions reacting with 2 moles of water produce 2 moles of HCl, aqueous, and 2 moles of hydroxide. And the delta H here was the delta H of reaction 1 times -3. All right, so that was due to the manipulations that we did to kind of put reaction 1 in this form. Now you'll notice when you go to add these 2 reactions together, first we get some cancellations, right? You have 2 moles of HCl here on the reactant side, 2 moles on the product side. So these cancel. We get another cancellation right here with 2 moles of HCl canceling 2 moles of HCl. So when you add these, all that's left over is magnesium, solid magnesium, reacting with 2 moles of liquid water, producing aqueous magnesium ions plus 2 moles of hydroxide plus hydrogen gas. All right, this is reaction 3. And you'll notice that the delta H for this reaction is equal to the delta H for reaction 2 minus 3 times the delta H for reaction 1. So to calculate, to use Hess's law, you've got to calculate the delta H for reaction 2, delta H for reaction 1, and then the kind of derivation steps are going to be the same for everyone. So you take delta H, the delta H of the third reaction is equal to the delta H of the second reaction minus 3 times the delta H of the first reaction. And that is how you handle that part 3 of the calculations. All right, Logan, you had a question on ELAB 7. Let me try to find... So, Logan, quick question. Ah, yes, 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 yes. Awesome, awesome. Sorry, I was at first I was uh, confused um, because I was confused because um, capital V um, is the unit volts, which is related to energy, is related to electricity. And I was like looking at it because I didn't write personally. I personally didn't write the worksheet for the experiment 7, and so I was sorry, I was confused because I was like, wait, did they include some stuff with like volts and electric current that I was unaware of? And so yes, so sorry, that was me needing some clarification, but now I know exactly what you're asking for, and we can totally do it. Okay, so let's take a look. Okay, so we're going to find the frequency and the energy of a yeah, totally of a wavelength of light that is, where was it, 656 nanometers. All right, now and so we want to find what is the frequency and what is the energy. Now, frequency and wavelength are related through their product, because the product of frequency and frequency and wavelength is equal to the constant speed of light. So first, to find frequency, we divide both sides of this expression by wavelength, and we get an expression that the frequency of light is equal to c, the constant speed of light, divided by lambda. Now, the constant speed of light is 3.00 times 10 to the 8th meters per second. And you'll notice we got units of meters, and our wavelengths unit was in nanometers, so we have a unit conversion to perform before we can plug this information in. So we put nanometers in our denominator, meters in our numerator. 1 nanometer is 10 to the negative 9th meters. So nanometers cancel, and our wavelength comes out to be 6.56 times 10 to the negative 7th meters. So we have 6.56 times 10 to the negative 7 meters is our wavelength. Now our length units cancel, leaving us with 1 over seconds, which, as you already pointed out, is the unit hertz for frequency. So 3 times 10 to the 8th divided by 6.56 comes out, and let's see, we got 3, we can keep 3 sig figs. 4.57317 times 10 to the 14th. Is that what it works out to? Yeah. Logan, you totally can. One thing you'll notice is that is the speed of light in nanometers per second. So if you have it in nanometers per second, you're good to plug and play. And the answer should come out to be the same anyway. Well, yeah. No, yeah. It totally should. All right. So here we have a frequency, keeping 3 sig figs. 1, 2, 3. This 3 is going to round down. The frequency of this wavelength of light is 4.57 times 10 to the 14th inverse seconds, or you could write it as 4.57 times 10 to the 14th hertz. All right, so that is the frequency. Let's take a look at our energy, and we'll actually need to keep the frequency at the ready, because energy, the energy of a wavelength of light, let's see, here, let's see, here, hang on one second. Sorry, one of the downsides to having a decent microphone is it can totally pick up your family's conversation through a wall. So the energy of a photon of light is equal to Planck's constant times frequency. Now Planck's constant is 6.626 times 10 to the negative 34th, and the units for Planck's constant are joules times seconds, and the frequency of our light wave, which we just found, was 4.57 times 10 to the 14th hertz, which is 1 over seconds. You'll notice that our time units cancel out, right? Seconds cancel seconds. And so we're good to multiply on through. 6.626 times 10 to the negative 34th times 4.57 times 10 to the 14th. So energy, the energy of our photon of light, comes out to be 3.028082, that's some weird symmetry, times 10 to the negative 19th joules. Now we can keep 3 sig figs again, just like 3 sig figs because of our frequency. Kind of when we, sorry, tripping all over my words here. When you count them off, 8 rounds up. So the energy of our photon of light will be 3.03 times 10 to the negative 19th joules. And that is the energy of a photon of light with a wavelength of 656 nanometers. Dude, I can totally do another one. Yeah. Okay, solid. All right, so the Rydberg equation is so we've got energy is equal to our Rydberg constant times 1 over the initial orbit squared minus 1 over the final orbit squared. And that constant, RH, is 2.18 times 10 to the negative 18th joules. It should be. Yeah, totally. So when you look at, so we've been given here an initial orbit of 3 and a final orbit of 2. So we've got RH times 1 over, let's see, initial 3 cubed minus, or sorry, squared, minus 1 over 2 squared. So this will be equal to RH times 1/9 minus 1/4. All right. So that's going to be 36. So this is equal to RH times 4 over 36 minus 9 over 36 if we give them common denominators. So our energy will be equal to RH times negative 5 over 36. All right, and RH, as we've just established, is 2.18 times 10 to the negative 18th joules times negative 5 over 36. Now something to remember about this is these numbers are exact, they're not measured, so they will not limit our significant figures in this calculation. So 2.18 times 10 to the negative 18th times negative 5 divided by 36 gives us an energy that is equal to negative 3.0, let's see, 3.03 times 10 to the negative 19th joules. So that is the energy release. We know it's released because it's negative for the transition that goes from the third orbit to the second. Claire, that is a great question. Yep. Okay, Claire. Sorry, your question about writing a net ionic equation with well, the amount of, okay, so okay, yeah, totally. Yeah, because if it's going from 2 to 3, it's absorbing energy to get there. Then if it goes from 3 to 2, it releases the same amount of energy, but it's spitting it out instead of soaking it in. Totally. Okay, Claire, you've been super patient. Thank you. Um, so Claire, um, so oops. Um, so Claire, I can totally show you how to write the net ionic equation for reactions 1 and 2. And I just wanted to let you know, if you want to see me do like the step by step for that portion of the calculations, it's in this video starting at 1 hour, 31 minutes, and 19 seconds. I'm not saying that because I'm trying to dodge your question. I can totally show you how to break down, do a net ionic when you have things that are insoluble, etc. And I'll do that right now. But I just wanted to mention it in case office hours ended, you wanted to see more. I did the entire step-by-step derivation earlier. So that's there for you, I guess is what I'm trying to say. Let's write the net ionic equation for reaction 1. So this is HCl plus sodium hydroxide producing liquid water and sodium chloride. All right. Now, when it comes to net ionic equations, first we got to break up every ionic aqueous compound, and we have 2 of them. We have sodium hydroxide and sodium chloride. All right, those are the only ionic aqueous compounds. So we need to separate them into their anion and cation pairs, and then once we have them separated, we will cancel any spectator ions. But first things first, let's break up all of our aqueous ionic compounds. So we'll have aqueous sodium cations plus aqueous hydroxide anions, producing water, liquid water, plus aqueous sodium cations and aqueous chloride anion. So this is the total ionic equation. Now, in the net ionic equation, we have to cancel all spectator ions. So we only have sodium is our one spectator ion here. So the net ionic equation for reaction 1 will be aqueous HCl plus hydroxide produces water, liquid water, plus chloride. All right, that is the net ionic equation for reaction 1. You'll notice, so let's take a look at reaction 2. So for reaction 2, we have solid magnesium plus 2 molecules of HCl aqueous produces aqueous magnesium chloride plus H2 gas. Now again, identify every aqueous ionic compound, and we only have one aqueous ionic compound, that is magnesium chloride. So we break that up into aqueous magnesium cations plus chloride anions plus H2. All right, now you'll notice that there are no spectator ions in this equation, which means that this is the net ionic equation. So that is how you break reaction 1 and reaction 2 into their respective net ionic equations. Yo, Sarah, you can totally ask a question about sig figs. All right, so let's take a look. Okay, so we've got 225 plus 250 plus 233.33. All right, so we add all these up. Let me grab my calculator. So 225 plus 250 plus 233.33. Okay, so our unrounded answer is 708.33. Now, the thing to remember about adding, the rules for adding in sig figs, is you want to go for the least precise. All right. And to find the least precise, you have to look at the last significant digit in every number. So 225 has its last significant digit in the ones place. 250 has its last significant digit in the tens place. And 233.33 has its last significant digit in the hundredths place. Sorry. And so whichever one has its last significant digit furthest to the left is the least precise. And so that is, for this sum, 250, which means that the precision, the last significant digit in our answer, must have the same place value as our least precise number. So our last significant digit needs to be in our tens place, and 8 is going to round up. So the answer after applying the rules for sig figs will be 710. You too, dude. Have an awesome one. All right. Great question. Kyle, great question. You too, dude. Have a good night. Alrighty, and that is going to do us for office hours tonight. Thanks everybody for coming out. It was actually a pretty full office hours. So which is awesome. Super glad to see some familiar faces who are usually up in here, and some fresh ones as well. Keep it coming. I'll be here. You know where to find me. Hope you have a great week, and I will catch you all on Monday, because Wednesday is Veterans Day. Later, dudes.